Astro BC Reddy Maths, CBSE 12th Maths. Now we are going to start application of derivatives. Number 1, the rate of change of quantities. The rate of change of quantities of y with respect to x at a point x equal to x is given by dy by dx. Now, increasing and decreasing function. Some rules are given. Let I be an open interval contained in the domain of the real valued function f. Then f is said to be increasing on I if x1 is less than x2. To be a f of x1 is less than or equal to f of x2 for every x1, x2 belongs to I. Strictly increasing function on I. If x1 is less than x2, in I, f of x1 is less than f of x2. For every x1, x2 belongs to I. Decreasing on I, if x1 is less than x2, in I, f of x1 is greater than or equal to f of x2. For every x1, x2 belongs to I. A function is said to be increasing at x0 if there exists an interval I equal to x0 minus h, x0 plus h. X is greater than 0 such that for x1, x2, x1 is less than x2 in I implies that f of x1 is less than or equal to f of x2. Similarly, we can prove that the strictly increasing, decreasing and strictly increasing can be clarified. Now, what are the properties of monotonic function? If f of x and g of x are monotonically, strictly increasing, decreasing function on a, b, then g of f of x is a monotonically, strictly increasing function on a, b. If one of the two functions, f of x and g of x, is strictly monotonically increasing and other is strictly monotonically decreasing, then g of f of x is strictly monotonically decreasing on a, b. Now, tangent and normals. The equation of the tangent at x1, x0, y0 is given below. Y minus y0 equal to m of x minus x0. Now m is nothing but slope of the tangent, dy by dx. The equation of the normal at x0, y0 is given by y minus y0 equal to minus 1 by m into x minus x0, when m is the slope of the tangent at x0, y0. Now, approximations. Let f of y equal to f of x, delta x be a small increment in x and delta y be the increment in y corresponding to the increment in x, that is delta y equal to f of x plus delta x minus f of x. The approximate value of delta y is nothing but dy by dx of delta x. So maxima and minima functions. Let f be a function defined on interval. Then number 1, f is said to be have a maximum value in 1 if there exists a point c in I such that f of c is greater than or equal to f of x for all x belongs to I. F of c is the maximum value and point c is a point of maximum value of f in I. If f is said to be minimum value in I, if there exists a point c in I such that f of c is less than or equal to f of x for all x belongs to I. F of c is the maximum minimum value, and at a point c is the point of minimum value of f in I. Let f be a real valued function and let c be an interior point of the domain of f. Then c is called a point of local maximum if there is an h is greater than 0. The value of f of c is called the local maximum value of f. Now c is called a point of local minimum if there exists h is greater than 0 such that f of c is less than or equal to f of x for all x in I, c minus h, c plus h. The value of f of c is called a local minimum value of f. Then f is a function defined an open interval I. Suppose c belongs to I be any point if f is a local maximum or local minimum at x equal to c. Then either f dash of c equal to 0 or f is not differentiable at c. Now, local maxima and minima. The first derivative test. Let f of x be a function differentiable at x equal to a. Then x equal to a is a point of local maximum of f of x. If f of a equal to 0, f of x, f dash of x changes sign from the positive to negative as x increases through a. If x equal to a is a point of local minimum f of x, if f dash of a equal to 0. Number 2, f dash of x changes sign from negative to positive as x increase through a. If f dash of a equal to 0 but f dash of x does not change in sign as x increases through a, that is, f dash of a has the same sign in the complete neighborhood of a, then a is neither a point of local maximum or nor a point of local minimum. In this case, x equal to a is a point of flexion. The second derivative. Let f be a function defined on the interval I and c belongs to I. Let f be a twice the differentiable at c. Then x equal to c is the point of local maxima. If f dash of c equal to 0, f2 dash of c is less than 0, the value of f dash of e is a local maximum value of f. If x equal to c is the point of local minimum, if f dash of c is equal to 0, f2 dash of c is greater than 0. In the case f of c is a local minimum, the value of f. Now the test fails if f dash of c equal to 0, f2 dash of c equal to 0. In this case, we go back to the first derivative test and find whether the c is the point of local maxima, local minima, or a point of inflection. Now we are going to start an absolute maximum, absolute minimum. If f is the continuous function on the interval I equal to a comma b, then f has absolute maximum value and f attains if at least once I, also f is that absolute minimum value and attains if at least once at I. If f is the differentiable function on a closed interval I and let c be any interior point of I, then f dash of c is equal to 0 if f attains its absolute maximum value at c. F dash of C equal to 0 if attains the absolute minimum value of C. Now we are going to find absolute maxima or absolute minimum. Find all the critical values of in the interval I, that is the value of x, whether either f dash of x equal to 0 or f is not differentiable. Take the endpoints of the interval. At all the above points 1 and 2 and calculate the value of f. Identify the maxima and minimum value of and foot of the values calculated in step 3. Then the maximum value will be the absolute maximum value of f and the minimum value will be the absolute minimum value of f. These are the absolute application of derivatives. Now, thank you. Subscribe it.